Hi, thanks for watching our presentation video called LoRaWAN Downlink Power Quality Evaluation for 3D Environments. In this presentation, we will start with the introduction, then we'll be presenting the mathematical model including the theory of the LoRaWAN network, then the simulation setup and scenario. Finally, we will present the results, conclusions, and the reference consulted. Low power wide area networks, LPWAN, are an important type of wireless communication that has been growing up in the last few years due to its applications and advantages. This network technology offers an improvement on the covered area, 10 to 40 kilometers in rural areas and 1 to 5 kilometers in urban areas. Also, it easy scalability at a low cost and a low power consumption. The principal three technologies using LPWAN networks are Sigfox, LoRaWAN, and NB-IoT. All of them offer efficient solutions to connect multiple smart devices. Mathematical model. The analysis implies the received power evaluation considering the shadowing effect, distance losses using the log distance and Okumura-Hara models, antenna gain as a function of the user position, and 3D end devices distribution. In the figure 1 is represent an hexagonal cells region, and in the figure 2 the simulation 3D environment. The model proposed is a non-deterministic model where slow fading losses and end users placement is considered. The equation 1 represents the received power for the log distance model, which depends on the transmission power, the antenna gains for the transmitter and the receiver, the distance between the antenna and the end device, the propagation losses exponent, and the characteristic Gaussian random variable of the log normal distribution, which models the shadowing effect. The equation 2 represents the gain level for the antenna at a 60 degrees sector. The outage probability represents the probability of receive or not the information in a wireless communication. Probability of a successful communication is obtained using equation 3. If the outage probability is higher, then the probability of a successful communication is lower. The equation 4 represents the mean power received. The Okumura-Hara model is based on empirical data that could be used to model the mobile propagation signals on rural and urban areas, due to its correction factor that it's helpful to adapt on the diverse analysis environments. Also, it uses other parameters that log distance do not, such as the antenna height, end device's height, and the frequency. The equation 5 represents the maximum path loss, which depends on the frequency, antenna height, end device height, and a correction factor. All of them are described in the other equations. For the simulation scenario, we use the model developed in a previous paper, which consider an environment divided in microcellular cells modeled as hexagonal prisms on a 3D scenario based on a discrete event Monte Carlo using MATLAB. The simulation occurs in a single cell with an adjustable radius, frequency, antenna height, and device height, considering a 120 degree sectorization. This sector matches with the antenna propagation pattern placed in the center of the cell. The table 1 shows the parameters used in the simulation, such as number of users, radius, frequency, spreading factor, bandwidth, transmission power, and sensibility of a LoRaWAN communication. Results. A comparison between both path loss models, Okumura-Hara in blue and log distance in red, was done using different ratios. In the figure 3 is shown the behavior of both models at a 100 meters ratio. The black line represents the sensitivity of the system. In this case, the result of both models is about the minimum power. Therefore, the signal will be correctly received. If the ratio grown, the outage probability for both models grown as well. For the log distance model, if the ratio is bigger than 300 meters, the losses will be greater than sensibility. In the Okumura-Hara model, the losses at 300 meters are approximately 80 decibels, which is further from the sensibility, 137 decibels, as shown in figure 4. To compare the log distance and the Okumura-Hara models, the results are shown in table 2 for the log distance, where it is shown that at distance for 200 meters, the outage probability is almost 42%. The table 3 shows the results for the Okumura-Hata, where the outage probability is lower. These results show that the Okumura-Hata model works better for an analysis of the behavior of the network at long distances. Finally, we present the conclusions and reference. We have observed for the long distance that the outage probability increases over the 40% when the distance is greater than 200 meters, which means that it's not a reliable technology for long distance. Considering that LoRaWAN was created for LP1 technologies, which its name represents wide area, long distance is not a model that represents its behavior. The opposite occurs with Okumura-Hata, which outage probability at the same distance of 200 meters is almost 1%. Therefore, in the study of LP1 networks should be used the Okumura-Hata model. These are the references used for this work. Thank you.